Okay, let's compare simple harmonic motion to circular motion. All right. Let's remember that simple harmonic motion, x, as a function of time, is equal to, oh, I got a little smudge there, is equal to the amplitude times the cosine omega t. That's the way that we wrote the position as a function of time. All right. Now, if we think about this, we've used cosine before to find out the x component of a vector when we graph it on the Cartesian coordinate, right? Let's say we got a little vector. Here's vector A. Probably not a good idea because I have amplitude there. Oh, actually, it works. It works. And if I want the x component, ax is equal to a cosine, here's omega, theta, theta, omega's up there, theta, okay? And that'll give me the x component. All right? Okay, let's clear this out. I'm going to draw my Cartesian coordinates again. There's my x position. And my y-axis, okay. And I'm going to see if I can get a circle here. This might work, it might not work. That's as good as I'm going to get. All right. Now, imagine if I draw a little, you know what, I'll do it with a pen. That's probably easier. Got a little point right here. Call that point P. And that's moving on the circle. It's moving on the circular path. All right. It's moving on the circular path at a constant rate. Its x position goes by, let's say that this distance is a. Usually we use r, but I want to have an analogy between amplitude and radius here. Would be a cosine theta. We also know that theta is equal to omega t. Omega is our angular frequency. T is the time if it's moving at a constant rate. So this could be rewritten as a cosine omega t. And y is equal to a sine theta or sine omega t. Okay, so there is my x component. There's my y component. And as it goes round and round and round, we can trace where it is in terms of x and where it is in terms of y. Well, don't you notice that this is the exact same equation that we have for the position of a harmonic oscillator? So a harmonic oscillator really is almost like a one-dimensional object that is comparable to the two-dimensional circular motion. Okay, it's like we have the x component, but we don't have the y component going right there. Okay, so let's say we could project our two-dimensional motion. Again, a little point P on a circle of radius a moving at a constant rate. We would see the shadow in the x direction. Say again, this is the x direction. We would see the shadow in the x direction following this a equals cosine omega t, okay? So there's this connection between the periodic motion of an object moving in a circular path at a constant rate and the periodic motion of a simple harmonic oscillator. Okay? Again, circular motion, you're oscillating in the x direction and the y direction. Simple harmonic motion, it's actually even simpler. We're only oscillating in one direction. Okay, we saw earlier that the period of a simple harmonic oscillator went like this: 2 pi times the square root of m over k. If you want the frequency was just the inverse of that. In circular motion, we've used this omega, okay? It represents 2 pi times the frequency. So we can rewrite this as, and we've done this before, we did this earlier when we derived this, omega is equal to k over m. So our angular frequency, again, is something we used with circular motion. Again, it works very well for equations in simple harmonic oscillators. That's about all I really can take away from this. A graph of t squared versus m doesn't pass through the origin. The spring has a mass and oscillates. I don't know how much that really adds to anything. But again, here's your position as a function of time. And again, you'll more commonly see the simple harmonic oscillator written like this. Okay. So yeah, simple harmonic oscillator, just basically taking the x component only of an object moving in a circular path.